Well, welcome back. Here I am. I forgot to say on last Thursday when I used that same music, Gary Walton, who's one of the authors of your textbook, that's his jazz group. So they're called Jazz Nuances. They're based in Davis, California. They play various jazz clubs. They play with the American Economic Association meetings in San Diego. So economists are people too. Hard to believe, but it's rumored to be true. Okay. So today we're going to start with how you read regression results. Quick survey: how many people have taken econometrics? Okay, so for you all, this is hopefully review. And for people who have not had econometrics, do not panic. I'm going to show you econometrics in 5 minutes, maybe 10 minutes or less. So that's where we're going to start. Then we've got a discussion about transportation and what's a boat, what's a train, what's a canal, all that good stuff, and some information about manufacturing, and that's on tap for today. Do y'all have any questions before we get started? Oh, and where's Patrick? Patrick, are you here yet, Patrick? No. So I will give Patrick the answer to his question when I see him. Anybody have any questions before we get started? Okay, no. So a lot of the journal articles that you'll be reading for this class involve regression results, because using econometrics is the way in which economists test the empirical data that we gather to figure out whether or not our stories, our hypotheses are correct. So being able to read econometric results is an important skill that you are expected to pick up in this class. If you've looked at the old midterms online, you'll see that every exam includes some regression results and asks you to interpret those things. The first problem set, which I'll pass out next week, is interpreting regression results. So it's an essential skill to being an economist. So the notion is this. Somebody specifies that there is some relationship between a set of variables, and we want to look at the relationship. So there's some relationship, and there we go. Which we can get specific about, or I can be generic. I have generic notes, I have specific examples. So we start out with some hunch that the variable y, which is our output variable, is related to x, and that would be our general functional form, where we say that y is some function of x. And then we're going to specify a particular functional form. So that functional form will be a linear form. So it will be, for instance, some variable some constant beta naught plus some other constant beta 1 times the variable x explains y. So we could say, I'm picking up things off the top of my head, which is never a good idea. If we were trying to look at, for instance, if we were trying to look at the determinants of consumption spending, we would say consumption spending, which is our dependent variable, the thing that we're trying to explain, is explained by or is dependent upon income. So that would be on the right-hand side of the equation. Or we could say it's dependent upon more than one variable. So we could have a functional form that was not just y is some function of x, but we could have our outcome variable is dependent upon some variable x plus some other variable y, and so on. So we specify that we think that the story that we're telling can be expressed mathematically through this linear equation that tells us how the various variables, in this case a boring, I put x down twice, that should be a z, the boring x and z, influence the outcome variable y. Then we gather a bunch of data. So we're going to gather a bunch of data on the x and the z and the y. I've got some example here. Let me find my example because my brain is not creating an example today, so I'll use an old example I created in the past. That's what it was. Suppose that we decided we wanted to see how many, we're going to do a science experiment. Good, because we're in a science room. And we're going to put into a beaker, we're going to put water and soda pop and vinegar. What happens when you add vinegar to soda pop? Do you remember this from your science fair class? Way back when? Yeah, exactly. So we're going to look and we're going to see how many inches of water, so that would be inches of bubbles, so that would be our outcome variable. How many inches of bubbles are created by combining water and soda pop and vinegar. And we suspect that if you just have water, how many bubbles do you get when you just have water? 0. Yeah. So we suspect that having water isn't going to make much difference. But we suspect that adding soda, or particularly adding soda and vinegar, is going to make this thing bubble up. I believe this was a science experiment that perhaps my son tried to do. You never know. I hated science experiments, just to say. That's the hardest part being a mother of an elementary school student, science fair. Anyway, so we say we're going to gather data. So we're going to go in the kitchen, we're going to do this over and over and over and over and over again. We're going to get a cup, we're going to pour some water in, we're going to pour in different quantities of water, different quantities of soda, different quantities of vinegar, and each time we're going to measure and see how many bubbles result from these different quantities. And so we're going to come up with this table or chart full of data. We're going to have columns, water, vinegar, soda pop, bubbles. Lots and lots of data. Then what we can do is we can take that data and we can drop it into the computer. How? Don't worry about. Drop it into the computer, and we can tell the computer, old buddy, old pal, we want you to take this data, and we want you to estimate this equation here that tells us how the inches of bubbles are related to the quantities of water and soda and vinegar. And we type regress. Regress, bubbles, water, soda, vinegar, we hit enter. Voila, it spits out results. It's done all this magic behind the scenes. You learn about the magic in econometrics. I don't care if you understand the magic. It's magic. Let it be. So there's a magic process, x prime x inverse x prime y, that results in these estimated coefficients. And then once you have these estimated coefficients, you're going to have, the computer's going to spit out, for instance, something that looks like this. That the inches of bubbles, I'm going to make up numbers. Inches of bubbles equal 0.02 plus 0.003 times the amount of water plus 0.5 times the amount of soda plus 0.9 times the amount of vinegar. So the computer has spit out these values, the estimated values of our constants or our parameters, the 0.02, 003, 05, and 09. That's the estimated form of the relationship. That's the estimated form of this relationship that tells us how water, soda, and vinegar are related to the amount of bubbles that are created. But it's estimated from the data that we put into the computer, and we don't know whether or not it's capital T truth. What we're interested in is not just from the experiment that we ran in the kitchen, where we may or may not have been recording things properly, and where we may have only done it 12 times, because after that your mother says, I think this is enough data. Right? We may not actually have the capital T true values of these coefficients, beta 1, beta 2, beta 3, that tell us, if we were to run this experiment 10, 100,000 million times in a good lab environment, what would we really get? What would be the true values of how water and soda and vinegar impact the amount of bubbles that you get by combining things and letting them bubble up and over? What regression results allow us to do is to get a bit of a handle on what the truth is, as opposed to the estimated relationship that we've just come up with. So what econometrics is about is econometrics gives you the estimated relationship, and it gives you some information that you can use to try to decide whether that estimated relationship is capital T true, is the actual true relationship between these various variables. So the way we do it is this. So you need to draw a little bit of your statistical knowledge. So we have some graph We usually just use the horizontal axes, but I decided I should label both. And on the vertical axis, we're measuring the likelihood, which the mathematicians would give some fancier name, the likelihood of some particular value. And on the horizontal axis, we have values of beta. And beta is the estimated coefficient. I had beta 1, beta 2, beta 3. If it bothers you, put beta 1 there. If you're cool without having a subscript, just call it beta. Draw a normal distribution. Find the mean, median, and mode. Lovely thing about a normal distribution. And below that, label that what's called beta hat. So the little caret on top, we call it beta hat because it looks like it has a hat on. Beta hat, that's the estimated value of the coefficient beta. That's the estimate. That's the number that dropped out of the computer. But the number that dropped out of the computer is an estimate of what the true, capital T true value of beta really is. And the capital T true value of beta lies somewhere within this distribution, this normal distribution of the possible values around beta hat. So it could be, given that beta hat, that's the value the computer spits out, it could be that true value beta could be someplace to the left underneath that normal curve. So this could be true beta. Or it could be somewhere to the right, could be true beta. So the true capital T truth value of beta could be right at beta hat, unlikely. Could be right at beta hat, but it could be to the left, it could be to the right. In any case, it's likely to fall someplace underneath or within that normal distribution. So the odds are really good that the true value of beta is going to fall somewhere between the two tails, the left tail and the right tail of that distribution around beta hat. So true beta, the truth value, if we had 10,000 million observations, the true value of beta, I'm calling it both truth beta and true beta, so it doesn't matter. Call it either one. Call it both. Truth beta falls someplace in that range between the two brackets underneath that normal distribution. The question that we can answer is whether or not the true value of beta is negative or positive, or we can't say. What we can get out of regression results is whether truth is a negative value or a positive value, or we don't know for sure whether it's a negative or a positive value. We get that by using what's called a t-statistic. So when we look at a regression result, and the regression result tells us that beta hat has an estimated value of 0.5, for instance, somewhere there is also going to be what's called a t-statistic. Now the t-statistic is the estimated value of beta hat divided by the standard error of that estimate. So the t-statistic takes that estimated value and divides it by the standard error. And the standard error, you may remember from your stats class, the standard error determines how diffuse or tight that normal distribution is. So if you have a big standard error, you're going to have a pretty flat and spread out normal curve. And if you have a small standard error, you're going to have a pretty tight and very steep kind of normal curve. So the t-statistic takes the estimated value of the coefficient, 0.5 in my example, and divides it by the standard error, which the computer also tells you. The computer tells you all of these wonderful things. And then we look at the value of that t-statistic. This is what you need to know. If the t-statistic is greater than 2, give or take, look it up in a book and it's like 1.9 something, something, something. That rounds to 2. So just keep 2 in your head. If the t-statistic is greater than 2, then we say that the estimate is statistically significant. Statistically significant is shorthand for saying it's statistically significantly different from 0. So the longer version of that is to say the estimate is statistically significantly different from 0. Which is to say that if that t-statistic is greater than 2, we know that the truth value of beta is not 0. Over on this side, do you guys have a question? Do you have a question, hon? No? Okay, so anytime you have a question, I'm really happy to take them. So just let me know. All right, so the true value, if the t is greater than 2, then we're really confident that the true value of beta is something other than 0. And all this stuff. And that the estimated value, that is, has the correct sign. So if the estimated value is plus 0.5 and the t is bigger than 2, we don't know what the true value of beta is, but we know it would also have a positive sign. If the estimated value of beta is minus 327 and the t is greater than 2, we don't know what the true value of beta is, but we're really confident that it has a negative sign. So what we get out of this is positive or negative. Are things directly or indirectly related? So let me show you with some pictures. Okay. So suppose that, once again, I'm going to, whoops. Yep. Yeah. I'll show you that in a second. What's your name? I forget. Prithvi asked about if t is less than 2, I'm going to show you that in about 2 slides. So let me show you this one first. So suppose, once again, along this horizontal axis, we've got possible values of beta. Draw yourself a normal distribution. The mean, median, and mode is your beta hat. And suppose that 0 lies well to the left of your distribution. So mark some point 0 that's well to the left of your normal curve. Then what the econometric results from the computer are telling you is that you can be 95% confident, t greater than 2. You can be 95% confident, which is pretty good, that the true value of beta lies somewhere in this bracketed region. So the true value of beta lies someplace between the lower tail and the upper tail of your normal curve. Both the lower and the upper tails are to the right of 0. And so you can be 95% confident, at least, that the true value of beta is something positive. So there we have a statistically significant coefficient that's a positive coefficient, and so the true sign of beta, we can be confident, is positive. Alternatively, it could be that you have an estimated coefficient. Again, draw yourself a normal curve, find the mean, median, and mode, and now mark 0 to the right of that whole distribution. You could have some estimated value of beta hat that is negative. And again, if your t-statistic is greater than 2, it means that you have confidence that that true value of beta, which lies essentially underneath 95% of your normal curve, that the true value of beta is also negative. You don't know exactly what it is. It could be with 95% confident at someplace in that range between your lower and upper brackets, but both your lower and your upper brackets are less than 0, so you're really confident that it's going to be a negative relationship, an inverse relationship. What if t is less than 2? Then you've got something like this. You've either got here's my beta hat. You could have that beta hat is estimated as a positive number, but 0 lies underneath your normal distribution. That 0 is within that 95% confidence bound. Or you could have, alternatively, another graph, again a normal distribution, again the mean, median, and mode is beta hat. You could have that the estimated value of beta hat is negative, but again that 0 lies within that 95% confidence region. If t is less than 2, it's telling you, yeah, sure, your estimated coefficient is positive or negative, but you have no clue whether the true relationship between these two variables is positive, is negative, or 0. It's such a weak relationship that you might as well assume that there is no relationship between these two variables. All right. Questions? We're ready for this thing. All right, so what we're going to do is we're going to put you in your groups. So once again, people along this edge, a row is a group. People here, the first, let me say 4. 1, 2, 3, 4 seats are a group. People here, 1, 2, 3 seats. 1, 2, 3, 4. What do I have? 3 seats. 1, 2, 3 seats are a group. Here, 3 seats are a group. 3 seats are a group, and along this wedge, each row is a group. We're going to pass out this exercise. We want you to work on it in your groups. We will be in the aisles to help you. We want you to do it in groups. We'll give you a little bit of time, and then we'll go over it together. Who still needs a sheet? I need one. This row, I think, needs some. Andrew writes this row. Does anybody else still need a copy? All right. When they calculate the t statistics, they're always taking absolute value. So those t's are absolute values. So the reason the first question is asking you what are those things in parentheses is that in some articles the authors will put the standard errors in parentheses, and in other articles the authors will put the t-statistics in parentheses. And you have to look around to find out where they tell you what's in parentheses. Sometimes it's at the top of the table, sometimes it's at the bottom of the table, sometimes it's in the text. You just have to look around.